Okay, test on Thursday during class time, right? Remember, reach out to me if you want to take the test online. I get an hour and 15 minutes. Yes, sir. In here, yep. We have the space, so there's no reason to get another room like we did last time. Hour and 15, I'll try to show up a little early, try to keep a few minutes late, but I can't go too crazy because some people might have class before, some people might have class after. And again, the one thing we want to do is make it as fair as possible. Can't use equitable anymore. You got to use fairness. So we just wanted to be fair for all people. Okay. And it's not going to really focus on the first few chapters where we did transformers and all that stuff. It's really going to focus on the concepts of machines, rotating EMFs, um, power flows, torque, all that different stuff that we talked about when we introduced AC machines, when we get those rotating magnetic fields. And then we applied that to synchronous motors and generators. Okay, that's the key. But with that being said, all the stuff that we learned, especially in the first couple chapters, right? The chapter one and the appendix A, when we did circuit analysis and we did three-phase power, a lot of those concepts are really important to get here because most of the stuff we're talking about are three-phase machines. Okay. So you really need to be mindful of the fact that that stuff, you need to know that stuff really well if you're going to be able to do well in this test, because you got to understand line quantities and phase quantities and when to use threes or square root of threes or not use them at all. Okay. So if you're struggling with that, go back to the previous material, come see me. But again, the square root of three is usually just for phasors. Otherwise than that, it's just a value of three. So voltages and currents are line and phase quantities. Everything else is either a single phase representation or an accumulation of all three phases. So power is three times a single phase. Voltage and currents are either square root of three or no square root of three, going back and forth. Impedances, because it's a delta connected, Y connected, and we're assuming equal, it's going to be multiply or divide by three. The only time you're going to use a square root of three for power is when you snuck in some line-to-line quantities, okay? But ultimately, it is based on three times the individual phase quantities. But lagging and leading are still important, and then also understanding how to calculate power loss, right? V squared over R, or I squared times R, or V squared over X and I squared times X. Remember, those have to be magnitudes only. So a lot of that stuff that we use at the beginning of the semester, we need to keep incorporating it because it is still relevant to what we're doing today. So let's talk a little bit about AC machines. And again, these get a little bit wordy, but AC machines uses, so the whole concept of an AC machine is it uses an AC or generates an AC voltage and current, right? And there are two types that we'll deal with. What we dealt with was the first one, which is actually not the most common one, but it's hopefully the easiest to understand, which is the synchronous machine. When you build an AC machine, usually the stator is the more power, where the more current comes in or out of, and you locate the windings on those to have electrical separation of about 120 degrees. Not mechanical, but electrical separation. So you physically build a machine, so where the windings are, you're separated by 120 degrees. All right. Now, 120 electrical degrees is different than mechanical degrees because mechanical is based on north and south magnetic poles. So whenever you start at a north and go to another north, including the original north, right, the one that you got back to, that is a mechanical operation. So if you only have one pole pair, you only have one north and one south, you have to rotate a full mechanical 360 degrees to get back to your north. If you have two pole pairs or four poles, that means north-south, north-south, you have to rotate 180 degrees before you get back to that north, okay? So why is that important to us? Because every time we go under a north, kind of restarts the sine wave. That's not exactly the case, but it just makes it easier to understand that. So if you restart at the north, you're basically starting your sine wave over, and then that means you've got a full 360 electrical degrees. So when you're determining the speed of operation, you can take your electrical frequency and convert that from radians per second to RPM. Everybody knows how to do that, right? No? If you're not sure, just always break it down to rads per second. How many revolutions per radian? So there's 1 revolution and 2 pi radians, correct? So we've got revolutions and we've gotten rid of rads. And how many minutes? How many seconds in a minute? 60 seconds and 1 minute. What you're left with is revolutions per minute. So you can just do the unit conversion just by, setting it up this way. So that's how we end up with 377 radians per second, because that's how much the system has to rotate around electrically to do a full 360 degrees, right? So if that takes the full 360 degrees mechanical, then the speed of operation is 377 radians per second. If it only takes 180 mechanical degrees, then the machine doesn't have to operate quite as fast to get back to another North Pole. So you drop the speed by a factor of 2. Why? Because you've no longer gone from 360, you went to 180, right? So you cut the number of degrees mechanically 1 in half, you cut the speed in half, and on and on and on until you can get really slow speed synchronous machines like hydroelectric dams. They run at pretty slow speeds. So this equation over here is pretty important for us to be able to convert back and forth. All right. And we can talk about mechanical frequency, but I don't know mechanical engineers. Do you ever talk about mechanical frequency? Maybe vibrations. But most of the time, I don't think mechanical, you don't want things vibrating mechanically, typically, not always. Because if something's vibrating like this, like ends up being a lot of force on the machine. So as much as you can, you like to avoid vibrations unless you're making, anybody know those compactors or something like that that's bouncing up and down. It's got a specific job. But most of the time, mechanical vibration it's a byproduct. You would prefer not to have it. But our mechanical engineering friends don't often talk about mechanical frequency. Okay. But electrical, that's really important to us because that's how the whole grid operates. So that's kind of the first thing. We do have on AC machines, this part right here, we have, and we started to introduce this a little bit about induction machines, but that's not, what we're going to be on this test. We're really going to focus on the DC windings. Most of the time on the rotor circuit is going to be DC because you want a constant north and south. You don't want that north and south changing its position other than by rotation. So using DC or even a permanent magnet, you do see some synchronous machines that are permanent magnet. They're not super duper common, but you can see that. But most of the time you go with DC windings. Okay. And then we moved into losses of machine because we're bouncing back and forth. So when we talked about all the equipment thus far, everything that we've done has been pretty much electrical to electrical systems. Now we're doing mechanical and electrical systems combined. And so those are hard to talk to each other, right? Because one is electrons flowing and one are forces or torques or whatever. And so the way that we can, sort of hold hands at the same point is power. Mechanical power and electrical power, they're both in watts. And so that's the way that we can talk to each other effectively and make sure we're on the same page. And so it's useful for us to do loss diagrams, right? Flow diagrams for power loss. In the top one, we can see that it is a motor. Why is it a motor? Because you have electrical power in and mechanical power out, right? That's the definition of a motor. It converts electrical power to mechanical power. And the input power is VI cosine theta. I don't have the 3 in there, or the square root of 3. I just kind of did it generically to simplify it, but keep in mind that input power either needs to have a square root of 3 or a 3 if it's a 3-phase system. Then you've got some losses to deal with. Well, you've got copper windings that go in the machine. Those are the stator windings. And right off the bat, we're going to have I squared R because the copper is not a perfect conductor. So we have some I squared R losses that we have to deal with. And at that point, all our electrical losses are on the stator. Now we can build a magnetic field and we can jump across the air gap and go into the rotor circuit. And the rotor circuit is going to include some mechanical losses and some actual I squared R losses in the core, the magnetic core, because we're inducing eddy currents. Most of the time, we'll categorize those as being part of the machine. You do have windings that wrap around the perimeter, but we'll assume that most of these are wrapped around the core. That's why this is converted power. It's converted to the rotor circuit. And this power over here, it's kind of hard to read, but this is induced torque times the mechanical speed of operation. There's our first comparison, because this is electrical power. Once we subtract I squared R losses, that is the converted power, which is the same as our induced torque times our mechanical speed of operation. So now we've been able to talk or communicate with our mechanical friends. Now we drop off some core losses because, again, we have eddy currents. Those are kind of considered electrical. And at this point, all the power that is converted is now going to be available for mechanical purposes or torque purposes. And we have some mechanical losses. What are mechanical losses? Losses, friction and windage, or bearing losses, right? We have to deal with bearings. Friction and windage losses is just the shaft that's rotating. You get some drag on the shaft. You have stray losses, which are just kind of random. You don't know where they come from. So we usually just tack them on the end because we're not really sure where they exist from, but they're pretty small. So we just tack it on the end. And then once we're all said and done, now we have torque that is available to the shaft to actually drive some sort of mechanical load. So that output power is our load torque times our mechanical speed of operation. Okay, that's the power flow diagram from a motor. Opposite of that is the next figure, which is a generator. Why is it a generator? Because the input power is mechanical and the output power is electrical. The generator converts mechanical power to electrical power, whereas the motor converts electrical power to mechanical power. And this piece of equipment can be the same piece of equipment. It doesn't need to be separate, because a motor or a generator can coexist in a synchronous machine. You just determine where the power is. So there really isn't that much of a difference in design between the two. So the input power, again, now is a mechanical torque. It's the applied torque times the speed of operation. We'll take out our stray losses. We tack them on the end. Now we're doing them at the beginning. Now we have some friction and windage losses, again, bearing losses. And now all the mechanical losses have been accounted for. Now we're going to go ahead and treat everything as essentially losses because of electrical current flow. Core loss is eddy current flow. That is a current loss. That's a loss because of electrical power. Now we're going to convert that power, because the mechanical power is usually coming in on should be coming in on the shaft, and that's the rotational that's going on the rotor. Now we jump across the air gap, and now we live on the stator, and all the power loss now has to be on the stator. That's all electrical energy. So the only thing we have to do is take out I squared R losses from the windings, and we've got our generator output power. Okay. So again, if you really get nervous, remember this has to either be 3 or square root of 3, 3, or square root of 3. Either one of those, if you're dealing with a 3-phase machine. So we started off with synchronous generators. That's where we really got into the concept of synchronous machines. But synchronous generators are still the primary source of energy, even though we have a lot of wind, we have a lot of solar, and they're taking bigger and bigger bites of the pie. The fact of the matter is, when you've got 2,200 megawatts of generating capacity in the state of Maine alone, and you compare that with all the wind and the solar, I don't think the wind and the solar are anywhere near 2,200. They're probably pushing 1,000 megawatts, but the reality of it is that that's nameplate capacity. What is the likelihood that the sun is bright and shining on the solar panels at the exact same time that the wind is rocking at 14 or 20 miles an hour? Pretty unlikely, right? Because usually heavy wind means bad weather. So you don't always get the same. But synchronous generators, you can have all those as long as the fuel is available. You can be cranking out full nameplate capacity with that. So we're going to have the concept that synchronous generators are still providing most of the power. And again, they can actually help with voltage, because we can change things on that DC field a little bit to make things happen. That's called the excitation. So how much magnetic energy you produce inside the machine is based on the amount of DC current or the field current that you drive into it. And that affects this internal generated voltage. That's the voltage that exists across the coil. It's not like an actual voltage source. It's just an induced voltage that is there because you've got a rotating magnetic field inside a set of windings. We normally operate saturated, and we saw that when we looked at all those generator capability curves. That's very common for us to operate that way. So we have to accept it, which means that our systems are not going to be linear. We actually have to use curves to go ahead and calculate some parameters. But with that being said, we can generate a pretty simplistic equivalent circuit model, which has an internal voltage here. And then I've got two inductors, one's leakage, one's synchronous, and then I have my armature resistance. This is like the full Monty version from an AC perspective. Don't forget over here, we have a field winding that provides the field, but we normally can neglect that because that has a DC input, right? That doesn't affect the AC system. There's no current flow from the DC system to the AC system, but the DC system does affect this voltage that we see there. So that's why sometimes it's relevant or important to show that, because it helps you understand in the background, there's this excitation system that a lot of people forget about, but is really important to make sure that generator works properly. How do you do it? Open circuit tests, short circuit tests, and these are done at specific field current levels. And then you just compare them. We had a couple homeworks on how to do that, right? We did one full-blown example in class. So I think it was 1,054 or 58 or 83 MVA generator. And we looked at the curves. And then you had a homework assignment where you had that was it 87 MVA generator or 312? I can't remember. There's too many numbers in my head. Where we actually saw open and short circuit characteristics. And you had to find a common value for your field current so that you could read voltage and current at each of those points and calculate your synchronous reactance, your X sub S value. We didn't have any field tests. We didn't have any DC field tests for the homework problem. So you just assumed everything was X sub S. You just neglected any contribution from RA. Usually they're so small, you can neglect it. All right. But that's where it's key. And if you need to, draw a curve with IF over here. And this is my open circuit characteristic. And here's my short circuit characteristic. This is V and this is I. And then just literally pick points on top of each other. If you have different curves, then don't get stressed. Just put them at the same point. Sometimes you have to estimate what the curves are. So remember, you have an air gap line that sometimes will help you because this is a line that is linear. It has a slope. So if you're trying to get, let's say, an unsaturated value, and you've got a field current value way up over here, well, if I pick that value, and if I get this voltage over here, that voltage is going to give you an unsaturated X value, isn't it? Just because you can extend the line straight up. That's the whole thing about the air gap line. The air gap line is if no saturation existed, what would the voltage be? That, by definition, is an unsaturated reactance. The saturated ones, the only way to get that is you're going to have to read that off the curve. Okay? So when you're looking at these characteristics, think about what you're trying to do. What is my OCC? What is my SCC? And can I, draw an air gap line and go ahead and get the additional data points I need? The DC test, like I said, that determines R sub A. But that's a simple test. You need the test results. And then if the machine is Y or delta, you need to do your calculations to figure that out. Short circuit ratio is just a number. Again, I don't see a lot of it being, yes, sir?
Should we expect to see DC test on the exam?
Yes. Why? Because see, this is in today's notes, right? I mean, online. This is
Have a look at it.
Aaron, is that yes or did you see that here? Yeah, I posted this so that I think somebody.
There you go, posted it.
Oh, that's okay. I just want to make sure it was posted because I know some people had asked for it. And I was just say, okay, maybe to make sure. But short circuit ratio is the ratio of the field current at rated voltage to the field current at rated current. Okay. I don't know what it's used for. I've never seen it, being used for anything. That was a SCR that we saw for the big generator, the one at Millstone. But oh no, was it Millstone or Surrey? I can't remember. There's too many. I work on too many of these. But you get the idea. You can calculate that, and then what does that tell you? It might be just telling you the quality of the generator, because how much do you have to excite something? Because if it's really heavily saturated to get that nameplate voltage, then maybe the short circuit ratio has to be, let's see, is it really big? Yeah, it might need to be really big, because if you're rated field current at voltage and you got to really push the machine hard, whereas the voltage, to get to that voltage, you got to push it really hard. Where to get the rated current, you don't have to push it as hard. that might be something where it tells you the quality of the machine. But again, I haven't seen too much of that. But literally, I would just go ahead if you need to calculate short circuit ratio, I would just write that down. We already talked air gap line, so that's if the voltage never saturated, you get that value. Synchronous motors are just like synchronous generators, except power is going in. So when you do KVL loops around your equivalent circuit, just be mindful the terminal voltage is always at its nominal voltage at an angle of 0, and then you can calculate the back EMF or the internal voltage just by subtracting or adding voltage drops. It just depends on if it's a motor or a generator. So if it's the equivalent circuit is up over here, if it's a generator, I have to make EF, at least I have to add those voltage drops to make it work, right? If it's a motor, it's plus to minus this way. So I have to subtract those voltages. Notice I did not say I have to increase or decrease the voltage, because the increasing or the decreasing voltage has to do with how the machine is operated. Is it supplying reactive power to the grid or absorbing reactive power to the grid? That's when we looked at our phasor diagrams and we saw, what is the magnitude of EA? Is it greater than VT or less than VT? If it's less than VT, it's an underexcited machine. If it's greater than VT, it's an overexcited machine, which means it's supporting the grid by providing bars. In either case, it supports it, but one is either providing bars or one's absorbing bars. Okay. Same thing with power. We can tell if it's a motor or generator just by looking at the torque angle. If EA is leading VT, then it has to be a generator. If it's lagging, then it's a motor. So you can just look at a phasor diagram. And that's why we spend so much time in this class looking at phasor diagrams, because they really tell you a lot of information about how the system is operating. Even in the generator, if you could get this information, you could tell a lot about it. But power system operation is always looking at magnitudes and angles to make determination of what's going on. There's a device out in industry called a phase angle regulator. Kind of interesting, right? They could have a phase angle regulator. Why would you want to control or regulate? It's another way to say regulate, right? Is control the phase angle, because you can control power flow. If you have a way of controlling phase angle, you can really do a big amount of control on the real power flow through a device. And so phase angle regulators are getting more and more common, even though they're crazy expensive and they're not something you can go to Home Depot and buy. They're hundreds of millions of dollars. I'm working on a project that wants to put in like a 300 MVA phase angle regulator at 138 kV, which is a little unusual for that low of a voltage. And they're trying to add it so that they can better control power flow in and out of Long Island. But it's going to be a huge thing, but you can directly control the power flow. So actually having this information and knowing about the phasor diagrams really helps you get a good understanding of power system operation. So that's what's kind of summarized here. The only other thing that we talked about when you start a synchronous motor is very different than starting an induction motor. You can just flip the switch, but most likely you're going to say bye-bye to your machine. I did that when I was a grad student a long time ago, and I tried to power up a synchronous motor, but I had it figured out as a motor. And I flipped the switch and that thing vibrated, and I was like, oh, what's going on? And then I started reading about it, like, oh, I need to have this thing spinning because it was rotating so fast at whatever the speed was, 1800 RPM, that this big hunk of mechanical whatever just couldn't latch on, it couldn't accelerate. And so to be able to start it, I had to do some other things to start it. But one of the things you can do, start it with a variable frequency drive, because if you run at synchronous speed, it's 1 hertz versus 60 hertz, that's 1/60th of the speed, it can probably catch up. You can start it with a mechanical system, which is you actually get it rotating a little bit, and then you flip the breaker and actually energize it that way, because once it's rotating, then you're in good shape. Well, the other thing too is some of the older motors have these damper windings or mortar windings, so you can sometimes start them that way. But that's hit or miss if you can always start it that way. So that's how you would start a synchronous motor. Don't ever start one across the line. And if you remember in this class, I actually showed you that pony motor, right? For the Northfield Mountain, that pump storage facility. That's a synchronous machine that either takes water from the upper reservoir and runs it down to the Connecticut River and generates, or operates in the opposite direction and sucks water up from the Connecticut River and takes it up to the reservoir. It's the same piece of same machine that does either direction. It just depends on what their need is. And so if you recall, there was a little pony motor to get that synchronous machine starting to rotate before you flip the breaker and actually got it rotated. You couldn't get it started otherwise. But I knocked off a question, right? Normally I have 6 questions. I only got 5. Find voltages and currents in a synchronous machine. That tells me is a equivalent circuit. Do equivalent circuit calculations. Remember, set the terminal voltage. Be careful if it's Y or delta if you're using line and phase voltages, so be aware of that. Calculate power flow in a synchronous machine. Looks like I'm looking at power flow diagrams, right? That might be really helpful. Given some test data, dun dun dun, open circuit characteristics and short circuit characteristics, find equivalent machine, X's and R's maybe. Calculate the speed of operation for an AC machine, 4 poles, 6 poles, 8 poles, how fast should it operate at? And then finally, determine magnetic fields given a stator configuration, the set of stator currents. That was based on, remember if we had a winding here and here, assuming current going in, we get a magnetic field, oops, going in that direction, right? And let's just put another one over here, 120 degrees apart. So this is winding 1, and this is winding 2. This is the magnetic field for winding 1. This is the magnetic field for winding 2. So the total is B1 plus B2, right? They had to be added vectorially. See, these are vectors. So you can say B1 at an angle of, oh, what angle is that? That's, let's say minus 120 plus B2, which is at an angle of, I guess we'll say that that's 30 degrees above. So minus 150 or minus 150, no, 180, 150, not minus 150. So you can add those vectorially, right? So being able to do those calculations, we spent a lot of time doing that. We did some MATLAB stuff and we put polarities, phases around. So if I said, hey, take phase A and B and swap them, you know, being able to redo this with the different currents and see if the rotation changes. I just showed 2 windings, but you should be able to do 3 windings, right? We did a lot of those. Yes, sir.
How would you tell rotation from that?
You can't.
Okay.
You need one set of currents, and then you need a second set of currents where the current has been rotated, meaning you're further down the ship. And then you see, oh, did the net magnetic field go from here to here? Then that's rotation.
Okay.
If it went from here to here, then it's in the opposite direction. And that's why we picked 30 degrees, if you remember in this class, because 30 degrees, you can see it went from here to here or here to here. If you pick 180, then it's in the opposite direction. You don't know, did it go this way or did it go this way? So I suggest doing 30 because it makes it kind of obvious. But if you want to do anything under 180 degrees, you could pick 12 if you wanted to. I don't care. You know, it just kind of gives you a sense of what's going on. Yes, sir.
And then how do you get the P value from it?
You have to be given some information to do this magnetic field. So what we were doing in the class is we just said you'd get some maximum B sub M based on a maximum current. So if I max or I magnitude was going in, under the biggest conditions, you get BM. And so then we said, all right, well, let's do the cosine or the sine of omega T because the current would change. So if I said, oh, there's a K parameter that converts IM to B sub M, so we just do K times B sub M, for example. Like if I said, okay, the value of K under the, case when you're producing the most magnetic field is pi. So then you'd say, all right, the magnetic field for B, if I get 10 amps going in, then the magnetic field will be pi times 10 magnetic field going out. Okay, so you would just do the conversion that way. Yes, sir.
Can we do an actual example of this? Yeah. I don't really remember this. Yeah.
You don't? We did many, many, many of these, didn't we? No, we did hundreds. I thought we did hundreds. All right, let's go to presentations. You didn't have a homework, or you did? I actually gave you a homework assignment, said try swapping A and C, remember? I didn't collect it, but I said try swapping it around. And I did give you an optional problem as well. So that's chapter 4, I believe. And we even did a bunch of work when we did MATLAB. Remember we did the MATLAB scripts where we said, okay, let's try it and then add these up and see what ends up happening. Let's see, this is not chapter 4, must be chapter 3, sorry. You don't remember this? Even did the color schemes, and I said that was a whole concept. Somebody was into archery, remember? And I said, oh, what do you call the quill and the point? You know what I mean? What do you run, head for the hills? Starting to ring a bell now?
I remember you.
So here, this actually was rotating if it wakes up. We actually did this, which shows you the calculations. We can do one still. I don't know why it's not rotating. It might be that it's supposed to rotate on its own, but it doesn't want to seem to do it. Here we go. Remember this? And you look at the colors and how they got bigger. The yellows or the reds or the blues got bigger or smaller, depending on what was happening with the current. And you see that black line in the center, its magnitude never changes, but it rotates around at a certain speed. Yes, sir.
I feel like I understand what's happening. I don't know how to put a formal answer. Like, what information are we trying to bring up? It's like, the E is the magnetic field strength.
B is the magnetic field strength. What you're trying to get is I'm building an AC machine, and I want to see if you all understand how those three currents, right, in these windings here, here, and here, how those three currents going into that machine are producing a magnetic field that has a constant magnitude and rotates around at a set speed. That's what I'm trying to get. So we did all that math, right, to show you how we get rotation. That's what's important. And all these arrows, right, and all these things, remember we did our right-hand rule, we put our fingers in and we wrapped around and our thumb pointed in an orthogonal vector.
Yeah, does it go in with the X or?
If I'm shooting an arrow at you, what do you see? The point or the quill? Yeah, so it goes in, right, at the quill, because that's going into the paper, and it comes back on the point. So let's go. Let's go over here. Look at A. The X, it goes in. My fingers point in. It wraps around because the coil of winding has to come back. It has to be a complete circuit. My thumb points to the right. So look at the red arrow in the center. It points in an orthogonal vector based on using my right-hand rule. Don't use your left. Well, it's not too much of a leap to use your other hand. Yeah, no? I mean, we can certainly do another one, but basically what we're doing is we're getting, this shows you perfectly here in even color coordinates. If I have positive current going in, so right at 0 degrees, I can see I'm getting maximum current going into winding A. A, right here, maximum current. That's the biggest X I'm going to get. Yes, sir.
So if looking at the red one, if the arrow's pointing that way, it means the current's going that way, right?
No.
The other way.
Nope. The current goes into the quill, wraps around here. The arrow is your thumb. That's the magnetic field that points. There's no current here, right?
In the opposite direction.
Yeah.
Right. So the current is this vector. This magnetic field that way.
But he said the arrow points in the direction of current.
Well, that's the
magnetic field. And the reason why that's important is could current flow through this piece of iron through the air gap? No, it can't. The magnetic field can, but the current has to flow through the winding. So you can see for A, right, we're at the max value of A, it goes in. Now we're going to move to B, which is the blue line. We have -5. So B is normally over here, but because we're on the sine wave where negative current is, it actually goes into B prime. Notice the X is on B prime, and it's smaller than the one on A. So my fingers point and my thumb points in the direction, and notice the magnitude of the magnetic field as a result of current in that winding is less. And then I do the same thing for C. C has the same half of whatever the value is. And so now instead of going into C, I go into C prime. Notice the smaller X. So using my right hand rule, fingers go in the direction of the arrow, come back, or the quill, come back on the point, and my thumb points down. So I get that value, and its magnitude is smaller. But it's always going to be orthogonal, right, to this one. So the red line is either going to go to the right or it's going to go to the left. It's never going to go up or down unless you switch where current goes in. Same thing for C. Let me show you my mad skills. And the same thing for B. I don't think PowerPoint has a built-in rule. I don't know. Yeah. But does everybody understand what we're doing here? That's where everything is based off of. Yes, sir.
And then this is an ACB1 or ACB or whatever they're right? So
No.
like ACB, no.
Nope. No, the currents, if you look at it, right? This one, we'll say that A is leading. And then which one comes behind? It's C, and then it's B. So not the windings, but the source is ACB. Remember the motor windings or the machine windings are just hunks of copper. You actually run current from each phase how you specify it.
Okay.
So the machine itself is not ACB. That's the source. Right.
Okay.
Are we good to switch, or we still want to see this? Because we can certainly switch, but I think this one does the best because it shows you the colors and it shows you relative magnitudes. So I can certainly do it myself. It just doesn't, and especially for TV land, it doesn't show, I think, the same impact, but I'm certainly happy to do it. I just want to make sure that everybody sees this. We good for this? Okay. So I'll just draw two windings so they won't get cluttered. So this is the A and the A prime, and the B and the B prime. Those are the windings. Okay. Now, depending where I am on my sine wave, this is A, and we'll say that B is 180 degrees out of phase. That's B. So if we're time t equals 0, both currents are there. So going into A is 0 current. Going into B is 0 current, right? So the net magnetic field, B sub A equals 0 and B sub B equals 0. So the net is the sum of those two equals 0. Why we don't want a two-phase machine, right? Two-phase winding is not a good thing. So let's go to 90 degrees, okay? So we see that BA is positive. So we've got maximum current going into A. So we'll show that as an X here and a point here. My magnetic field, this is BA when we're at 90 degrees, right? So now I'm at B sub B, or I'm trying to calculate my B sub B, which tells me I have negative maximum current. So here's my X and here's my O. So when I do my fingers, I get a B sub B here. So my B net for 90 degrees is equal to BA, which has an angle of 180, plus B sub B, which has an angle of minus 90 or positive 270. These magnitudes are the same. So you could just say B max, right? Because they're at their max currents at 180, plus B max at an angle of minus 90. To figure out, over here, this is where it gets a little harder. So we'll assume that they're at both 0.5. So again, this is that T, and I'm not going to say time. I'm going to say the equivalent of 90 degrees. Everybody understand that that's seconds is the time, but whatever the frequency is, it's 90 seconds. Now we're going to say that they're both at 45 degrees. When is the sine wave at 45 at 0.5? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. So 30 degrees, isn't it? So this is T equal 120 degrees. So now I'm over here. So my A still exists and my B still exists. Now my B sub A, it's going to be over here, but it's going to be a smaller X value. This B sub A is smaller in that direction. B sub B is still a negative number, and it's negative 0.5, but it's a smaller number. So B net is going to be equal to BA, which is at an angle of 180, plus B sub B at an angle of minus 90. Well, we have half the current, so we're going to assume that we're not in saturation, because we got to have, got to make it simple at some point. So we're going to assume that those are half the magnitudes. BM over 2 at an angle of 180, plus BM over 2 at an angle of minus 90. Now we can check rotation. The problem is we can't do a great job of checking rotation because the magnitudes are going to change, but the magnetic field is going to be less, right? Because we're adding the same numbers. So this is not a realistic machine, but it simplifies the analysis. So looking at a two winding machine, you can see why two windings don't work. That's why in your house, a lot of times you have to have a start capacitor and a run capacitor to give you a phase shift between them. Is that what you're all looking for an example, or? No, Aaron said no. Well,
I'm still confused on what direction the magnetic field goes relative to the current. You can hold a hand either way.
you can. That's right. But which way is the current going?
Like with the arrows, or two arrows like I and D.
I and B. I don't need to, and I'll tell you why. Let me delete this. See if I can erase this. And I'm not trying to belittle your comment. It's what I'm saying is the direction of the current, because I got people in TV land, it's going here in the X. So current is going here, it's going into the machine, and it's coming out here.
Right. So current's flowing from A to A prime right now. So magnetic field goes that way. Well,
It goes in like this, and wraps around, because it has to come back, and my thumb points in the direction of the vector that is orthogonal to the winding.
will come forward with it. Going around them.
Right.
That's the current, and then we're going to get to go from that. So it is. So the current's going like that.
It has to, because it's a winding, right? So it has to go out and then come back to the source. Hold on, TV land. The other way is you can just do this, right? Stand here. This and this.
Yeah.
But you can see that too. If you look here, you can see the X and the dot for the red, and then the corresponding vector, B sub A. Make more sense? You want to explore this more, or? I'm not exactly sure. Because if I put up another example, it's going to be the same thing. So I don't know how helpful it is. It's just something you got to do, and you got to try to draw pictures and do it that way. But like I said, this I think does a really good job of showing it, sort of just generically. And then you can see a very specific one. It shows you at t equals 0. Here are my currents, right? Then just plug those into the windings, A, B, and C. Then you can see 90 degrees. Here are my 3 currents. Plug those into your formula, and that's how you get those angles. You don't see B sub A over here. Why don't you see BA over here? You ask that question. Why is BA not there? Did I make a mistake? Is it hiding behind the black line? Yeah. What's the current going in winding A? 0 amps. How much magnetic field are you going to get when you have no current? 0. So it disappears. That's why if you look over here, look at what happens at the lines. Sometimes the blue disappears. Sometimes the red disappears. Sometimes the yellow disappears. And if you did it for all the angles, if it was continuous, you would see those shrinking all the way down until they got to 0 and then increasing slowly. Right now, they're in sort of more discrete steps because you don't want to do 500 of these, but you can see that here. The problem is this is moving, so that's why it's hard to tell. But if you look at the X's, and you can pause this video when you watch it at a later date and time, you can pause it and you can actually monitor and see how that works. You want me to stop it? Because I can see you guys are using hands. Let's go this. Just look at this one. This one's paused for you. Better? You remember this? We did cover this, right? You don't remember this? Uh-oh. Oh, good. We did have this on a homework. I did give you that. I even generated, if you remember, there was a bunch of MATLAB stuff. Where is I guess I must have closed it by accident. But if you look under our MATLAB scripts, which I know you don't super duper care about too much. AC rotating magnetic field. Go back to 2/18/2025, just over a month ago. These are when we did these. These 3 scripts, we built them and we kept changing them, right? We started out with generic, then we did AC, and then we did AC, then BC. We did all those during class where we changed those angles. Want to spend more time on this, or? Maybe.
Why?
As long as you explain how you got there, you can't just say from MATLAB. You can use it to check your work. But remember, you have an option. You can use MATLAB or the calculator. Not and. Let's see. So let me look under content. I can certainly, so that was a nice thing about opening up the files because it was 2/18. See, y'all trying to diss me, right? Say, no, there's no way you did all this stuff. You never presented this. When did I put this up there too? 2/18. This is all ad lib.
So long ago.
What's that? No, it's okay, but I mean, hopefully it's like, oh yeah, I think we did do this. My concern is everybody's like, I have no idea. I don't remember doing this at all.
No, I remember doing it now. Feel better. Did not remember.
Okay.
Exactly. I still don't get how to do the math for a 3/5 one. I'm trying to do the problem that's like on the congested problems for one of the homeworks.
Yep.
And I'm not able to get it. But it was. It was homework 5. Or 3, sorry. Homework 3.
Let's see. I do have the,
The suggested ones don't have to work.
okay. So let's see.
The top one, 5 is the actual bottom answer, which is the calculation part.
Okay. So draw the corresponding magnetic field for positive current flow into the winding. I'm not looking for anything other than positive current flow into the winding.
I understand that. It's question number 2.
Oh, number 2.
I don't get how you solve the rotation.
Okay, so now what we need to do is we need to go to the amount of rotation has been 90 degrees, right? So probably the best thing to do would be to use these values here.
That's what I was trying to do. You work it out. That's what I've been trying to do.
Yep. I've gotten different ones. I don't remember what they were, but let's see. So BA is going to be, let's see. Actually, I'm kind of doing it backwards. I think those aren't those values. I think it was for T equals 90 degrees. It looks like, well, okay. If we do it whatever value, so we'll do the ones that are there. So we said IA at T equals 90 degrees is 0, right?
Yeah.
IB is equal to minus 0.5. And these are just some, minus 0.5 or whatever the magnitude of current is. It could be 1,000 amps, it could be 1 amp, we don't know. And then IC is equal to positive 0.5, right? This is at 90, isn't it? Right here?
Isn't that, wouldn't it be square root of 3/2?
No, we're using these. Oh, 0.866. Yes, you're right. So square root of 3/2. Yep, square root of 3/2. Positive square root of 3/2. All right. So now we know that we have 0. So we know that BA is going to be 0. We're done. No current in, that's done. To get B sub B, we have to go ahead and run our current in the direction as shown. Well, this is the B winding, and if positive current was going into B, our current goes in here. But in fact, it's negative current. So what we're going to do is we're going to end up with a magnetic field, B sub B at 90 degrees, because it's negative current, right? It's not going in B, it's going in B prime. So B sub B, we're going to say that it's the square root of 3/2 times whatever the maximum magnetic field is going to be. We don't know what it is. We don't really care. It could be 10. It could be 5 million. It doesn't matter. Go ahead.
Where is the square root of 3/2? That's the one that we're being 6 there.
Yeah. If you were to do a sine wave, so this is a phase shifted sine wave. What's that? Well, so this is a cosine wave, right? If you phase shift a cosine wave by 120 degrees, plus or minus, you'd end up with a plus or minus square root of 3/2 if this omega t was equal to 90 degrees. So it's basically the cosine of plus or minus 30 degrees.
Would you have to give us these graphs then? We want to write down.
You can do, as long as you specify what you're using, that's fine. You can either use these or you can use sines. Totally up to you. Or I might give you currents. Right? So
you give us like the rotation that needs of a current at that rotation, like at that 90-degree rotation.
no, you should be able, because it depends on what you pick, right? What if you picked 10 degrees? What if you picked 20 degrees or 30 degrees?
So we would be able to pick our own rotation. Section
As-
that's going which direction.
Right.
Okay.
Yep. I would pick easy ones. I would probably start with 0, right? Because that's an easy one usually. And then either do plus or minus 30 degrees maybe. But you can pick whatever you want.
So you basically just be doing same calculation twice.
Same calculation, but the hard part is, remember, your fingers have to wrap. Okay? Can we continue on with this, or? So everybody understand where I got B sub B? So one thing I need to do is I have to add an angle, right? Because this is a vector. It has a magnitude as well as a direction. So I'm going to state that that angle is minus 60 degrees. Look about right. And the last one that well, let's see. So yeah, so I think that that's because the way you would do that is this is 180 degrees. And if we add, so we'll assume that that's 30. So yeah, so we do that. Now to do B sub C, which is going to have positive current going into the C winding. So positive current goes in here. My magnetic field is going to be in this direction, B sub C here. You notice that they're either in the same direction or in opposite directions of those base ones, right? Because the current is going in the positive direction. Okay? For B sub C, so it lines up with the original one if there was zero current going through. Over here, B sub B is in the opposite direction of the original one because it's a negative current flow. So now B sub C is square root of 3 over 2 times B sub M. And then the angle here is going to be, let's see, minus 120. Now add them together. Can you add those vectorially? B net is going to be equal to sum B sub M times square root of 3 over 2 at an angle of minus 60 plus square root of 3 over 2 at an angle of minus 120. You can enter that number in your calculator, right? You just factor out the B sub M. And there's no B sub A, so it's 0. You know, I included it, but it happens to be 0. So you're definitely going to get the 1.5 B sub M. I would think it'd be at minus 90 degrees because if you look at these two, Wyatt, you see how they're the same magnitude and they're sort of 30 degrees apart from the minus 90. So they should be going in this direction now. Did you not get that?
Well, it's really interesting. Your answer says minus 90 and the one that we have says 0 degrees.
Oh, huh.
Yeah, it's 0 degrees. Oh, yeah.
I don't know. Maybe this is the PDF. Maybe they'd put up a Word file. I don't know. I'll update it then.
He's just looking at the homework because of the problem. That's what the answer is. Well, all the answers.
Oh,
Yeah, the different diet.
so oh, I gotta go back over here. Sorry. That might be a typo. Yep, should be minus 90.
Other things like
Well, he could have used different starting currents too, right? He didn't have to have the cosine waveforms that I had.
Well, I used the cosine.
Oh, well, then I don't know what to tell you. Let me just print this and I'll update this file, this image.
So you have to start your. You can use a different line than I did. I thought the 0 degree line technically would have been the horizontal, but you used it from B to B.
I guess I'm not quite following. Hold on, let me do this real quick. I just want to make sure that. Okay, so say that again.
So I had done the 90 degrees from like a horizontal, right, a line that went straight through the HA,
So I don't think it's saved, so. Because the file is open. Thought I closed. I don't know what happened. That was weird. It didn't seem to write it, but I will write it again anyway. And so what were you saying? I'm sorry.
So I was saying that I thought the 0 degree line would have been like straight horizontal.
Yeah, I think that's what I had.
You did from B to B. Uh,
I did from B
you did
to
a 30 degree.
Yeah, because you were measuring for B sub D,
Yeah.
magnitude going down.
This one right here is 120, minus 120, right? And the one that we got over here is minus 60. Is that not what you mean?
So I was using like a rotation of 90 degrees from here, like from straight, like going straight across, like this rotated 90.
Oh, yeah. No, definitely not.
So
Yeah.
it's supposed to go from,
It's the current. It's what the current is rotated.
okay.
That's why,
So what I had like an angle of 210 and an angle of.
yeah, no. It's not, the only thing that is rotated actually is the current. So that's why you go from 0 to 90 degrees here. That's the current that gets rotated, not the actual physical one, because that doesn't have a lot of meaning, right? When you say physical rotation on the diagram, it's what the current is doing. That's what's dictating.
And then in yours as well, you use the positive version of both currents, but I thought it said that you need this in negative.
No, I did the negative, didn't I? Because I said this would be the positive current going.
In the work that you just did. Like the work that you just had, I think you changed the angle.
I changed the angle. I had positive minus 120 and minus 60, right?
Yeah.
Right. Yeah. But the reason why you have to do that is because with vectors, right? You always have a positive magnitude and then you shift the angle. So I did BM plus and plus, but it was minus 120 and minus 60. That's how I ended up with it. Feel better? Feel worse? What happened? Was this hard stuff? Well, you got 2 days. You had break. How else? What other questions do you have? How can I help? You got about 10 minutes-ish.
For the equivalent circuit stuff, are you just gonna, do we just want single phase? Is that what you're gonna ask for, just a single phase instead of a whole?
Yeah, you always in a 3-phase class, you almost always represent it as a single phase because all the other phases are the same. So why draw 3 when 1 is sufficient?
Okay.
Yeah, it's pretty rare that you draw all 3 phases. I mean,
Yeah.
not unheard of, but it just why it's busy work. You know, you're just drawing the same thing 3 times instead of
Yeah,
once.
I guess, you know, my only thought was that it's going, you're just doing a phase instead of a line to line of the.
Well, and keep in mind, I have a resistor and an inductor. Those aren't line-to-line resistors and inductors. You only have a single phase resistor and a single phase inductor. Right?
Yeah.
So we have to represent those as single phase quantities. We can't throw in line quantities in there and get the correct results. We have to do everything on phase relationships.
Okay. Which changed or something.
Yeah, it's delta or Y. But at that point, a line-to-line voltage on a delta is the same thing as the phase voltage. So you still are doing everything as phase, but it's not wrong to say that this voltage is a line voltage. It just happens to be the same as the phase voltage. See what I mean by remembering that stuff from previous chapters? Kind of important. Yeah, so the only thing I would say to do this is just keep practicing, you know, how to do those, use your fingers, wrap around. That'll help. Rewatch the video from 218. Try the MATLAB scripts if you like playing with MATLAB.
Is it a practice problem we can do on our own time?
I would go back and I would try this at 30 degrees, 60 degrees, 45. I mean, once you've got, if you can do the ones that we've done thus far, or go back over here, this one will really tax you because when we said do the homework, I showed you how to do this one as configured. Then I said swap A and B. Then I said swap B and C. That's what we did in class. We did a bunch of these. So if you can do it for these and just do it on your own without any help, and then swap any two phases, you should be in pretty good shape to be able to do these.
Also, we're swapping A prime, B prime.
No.
No?
No, I'm swapping where, remember, this is one continuous winding. So in the real world, this is a piece of copper that goes from here back. So when I swap A and B, I am swapping B to B, B to A, and B prime to A prime. I have to, because that's the current flow, remember? It's current going in, then coming back. So that's A phase current. I'm swapping A and B and A prime and B prime.
Yeah.
So I'm being a stickler, right? I'm not just swapping A and prime and B prime. I'm swapping all four.
A prime can be lined up with B.
No.
I don't like it.
No, you just said A prime and B prime. That's what confused me. It's got to be all four. No, you're physically moving the current, so which means you're taking the motor apart. You're taking the A phase, the wire that carries the A phase, and the wire that carries the B phase, and you're switching them. You don't have to worry about the other end and why it might say. Noah might say, "Why are you doing that?" That's because they're internally connected. It's either a Y or delta. So when you swap them around, they kind of automatically get swapped around. But in reality, what's happening is the current is coming back through there on the A prime or B prime line. Now, do you feel better or worse? Well, it wasn't meant to scare you. This was meant to help you feel better. Okay. Yeah, this wasn't meant to be a surprise. This was all stuff that we've been covering, right? Maybe it's been a minute. But go back and rewatch the videos, try to do some practice stuff. It should all be there. We got a little more than 5 minutes. Any other questions? You had enough today? Yeah, it's important to know this stuff because this applies for both induction and synchronous machines. So it's used extensively. Any AC current, even if it's a two-phase machine, because we started off, and we could certainly build a two-phase machine. We can just see doesn't work all that well, right? We get zero torque, and sometimes we don't get rotation. So in real world AC machines that are single phase, you have to put a capacitor in to get a shift. That's how they do it. But it's not smooth torque operation. It's just designed for cheapness. All right, anything from TV land? All right, have a great day. I'll see you, if I don't see you soon, I'll see you on Thursday at the test. Take care, everyone.